Bismillahirrahmanirrahim. In this lecture, we are trying to solve problem 4.26 from Applied Thermodynamics by McConkey with Dr. Abid Hussain. So, the statement of the problem is in an open type feed heater steam enter at 15 bar and 200 degrees centigrade. The feed water enters the heater at 130 degrees centigrade and leaves the heater at the saturation temperature corresponding to the pressure in the heater of 15 bar. Calculate the mass of steam entering per unit mass of feed water entering the heater. Calculate also the loss of exergy of the steam per unit mass and the effectiveness of the heater. Assume that there is no heat loss from the heater at that the atmospheric temperature is 20 degrees centigrade. State any other assumption. So first I explain the concept of the problem. So let me draw a simple sketch. This entrance is for this is heater, this is feed heater. This is steam entering to the feed water, to the feed heater. Steam entering, entrance. This entrance is for feed water entrance, and after entrance to the feed heater they are mixed, and this is exit of the mixture of steam and feed water. Steam plus feed water, steam plus feed water exit. So let mass of steam entrance to the feed heater is ms, mass of steam, and mass of feed water entrance to the system, to the feed heater, is mf, mass of feed water, and here is the mixture of S and F. So this is exit is mass of steam entrance plus mass of steam exit. This is ms plus mf. Similarly, let temperature of steam entrance is T1, pressure of steam entrance is P1, enthalpy of steam entrance is H1, and entropy of steam entrance is S1. Similarly, feed water entrance temperature is T2, feed water pressure entrance pressure is P2. Similarly, enthalpy is H2 and entropy is S2, and temperature of exit mixture is T3, pressure is P3, enthalpy is H3, and entropy is S3. So now again listen the problem. In open time feed heater, steam enter at 15 bar. Steam enter at 15 bar, this is P1. So given data, steam, first steam entrance to feed water, to feed heater, steam entrance P1 is equal to 15 bar, and T1 is equal to 200 degrees centigrade. The feed water enters the heater at 130 degrees centigrade. Feed water entrance. Feed water entrance. Feed water entrance. Here T1 is given to us. T1 is equal to 130 degrees centigrade. And leaves the heater at the saturation temperature corresponding to the pressure in the heater and the entrance in the heater at 15 bar, corresponding to the pressure 15 bar. Exit. This is the exit. So exit of the mixture at the exit pressure P3 is given to us is 15 bar. And at the end of the problem, we are given atmospheric temperature T naught. T naught is 20 degrees centigrade. T naught is 20 degrees centigrade, which is equal to 20 plus 273 Kelvin, which is equal to 293 Kelvin. Now required data. Required is calculate the mass of steam entering per unit mass of feed water. Now the mass of steam entering is ms and mass of feed water entering is mf. So first required thing is mass of steam entering to heater divided by mass of feed water entering to heater. Feed water entering to heater, which is equal to ms divided by mf. Second thing is calculate also the loss of exergy of the steam per unit mass. Number 2, calculate loss of exergy of steam. Loss of exergy of steam per unit mass. Per unit mass, which is E1. I name this. I gave name this E1. And number 3, effectiveness. Loss of energy of steam per unit mass mean steam. This is steam entrance, and this is mixture of steam and feed water exit. So how many exergy is lost in entrance and exit? Entrance of the steam and exit of the steam. So this is E1. And third, the effectiveness of the heater. Effectiveness of heater. Effectiveness of heater. Now there are some assumptions. First assumption is given that no heat loss and gain. It means that Q is equal to 0. And it is given in the statement that assume any other assumption. So second assumption is change in kinetic energy is equal to 0. And third assumption is change in potential energy is equal to 0. Now we start the solution. In solution, first we find enthalpy and entropy at entrance of the steam, entrance of the feed water, and exit of the steam. So from this we can find ms divided by mf, our first required value. So at state 1, at entrance of steam, at entrance of steam to the heater, at entrance we are given P1 is equal to 15 bar and T1 is equal to 200. First we check that this is superheated region or wet region or saturated liquid or vapor form. So first we find saturation temperature for this pressure. So from saturated steam table at pressure P1 is equal to 15 bar. Check saturation temperature, which is 98.6 198.3 degrees centigrade. As T1 is equal to 200 degrees centigrade is greater than saturation temperature, which is 198.3 degrees centigrade. So steam at entrance are in superheated region. So we will use superheated steam table to find H1 and S1. So from superheated steam table at pressure is equal to 15 bar and temperature T1 is equal to 200 degree centigrade. H1 is equal to H1 is the steam at entrance. H1 is equal to 2796 kilojoule per kg. 2796 kilojoule per kg. And S1 is equal to 6.452 kilojoule per kg. 6.452 kilojoule per kilogram per Kelvin. Now we are going to find H2, H3 and at the exit of the mixture. Now mixture mean steam plus feed water. Now steam plus feed water exit. It as we are given that at exit the feed water is saturated liquid. So this is on saturated liquid line. So this will be on the saturated liquid line. So as feed water leaving the feed heater is saturated So it will be unsaturated liquid line, unsaturated liquid line. So from saturated steam table, from saturated steam table at pressure P3 is equal to 15 bar, H3 is equal to HF, which is equal to 845 kilojoule per kilogram, and S3 is equal to SF is equal to 2.315 kilojoule per kilogram per kilo. Now per feed water entering the heater, now per feed water entering the heater. Now entering the heater is before saturated liquid, and this is the PV diagram. Pressure in bar and specific volume in kilojoule per kg. This is PV diagram, and feed water exit is unsaturated liquid line, and entrance is before this line. Before this line means this is in subcooled region. Is feed water entering to the saturated, entering to the heater is before saturated liquid line, saturated liquid line, before saturated liquid line. So it will be in subcooled region. So it will be in subcooled region. So from steam table of subcooled region at temperature is equal to 130 degrees centigrade and pressure is equal to 115 bar. This is our assumption, because pressure at inlet, steam pressure at inlet is 15 bar and mixture pressure at exit is also 15 bar. So we assume that the pressure of feed water is also 15 bar. This is our assumption. So from subcooled region steam table, at these values H2 is equal to 546 kilojoule per kilogram, and S2 is equal to 1.634 kilojoule per kilogram per kilo. Now we can find MS, mass of the steam entering the heater, from the energy balance equation. Energy balance equation, again I draw this diagram. This is mass of steam entering, this is enthalpy of steam entering, this is mass of feed water entering, mass of feed water entering to the heater, and this is enthalpy of feed water entering. This is mass total mixture, MS plus MF exit, and this is H3 enthalpy exit from the heater. So from the mass balance equation, from energy balance equation, from energy balance equation, MSH1 plus MF H2 is equal to Ms plus Ma per H3. These are for entrance, these values, and these values are for exit. Now, putting the values in this equation and find Ms. So, Ms enthalpy at 1 is 2796 kilojoule per kg plus mass of feed water exit is 1 kilogram per unit mass. This is given in the statement is per unit mass. Mass of steam entering per unit mass of feed water entering. This is unit mass. That means that this is 1 kilogram. And H2 is equal to 546 kilojoule per kilogram is equal to Ms plus Mf. Ms is required to us. Mf is 1 kilogram. And to H3 is 845 kilojoule per kilogram. Now further simplify this. So this is 2796 ms kilojoule per kg plus this kilogram will be cancelled with this kilogram. This value will be 546 kilojoule is equal to multiply these values. So this will be 845 ms kilojoule per kilogram plus multiply 1 kilogram by this value. So kilogram will be cancelled with kilogram and this will be equal to 845 kilojoule. So 2796 ms kilojoule per kilogram and write this value on this side. This will be equal to, because this is same, 845 ms kilojoule per kilogram is equal to, this is 845 kilojoule minus 546 kilojoule, and other side will be minus 546 kilojoule. Now further simplify. 2796 minus 845 is equal to 1951 ms kilojoule per kilogram is equal to 845 minus 546 is equal to 299 kilojoule. To find ms, divide both sides by 1951 kilojoule per kg. So ms is equal to 299 kilojoule divided by 1951 kilojoule per kg. So this kilojoule will be cancelled with this kilogram, and double division will be in the numerator. So ms is equal to 299 divided by 1599 is equal to 0.1532 kilogram of steam. So we are required ms divided by mf, mass of steam entering to the feed heater divided by unit mass of feed water exit. So this will be equal to 0.1532. This is kilogram of steam entering to the feed water. And unit mass means 1 kilogram of feed water exit. So the final answer will be equal to 0.1532 divided by 1 is equal to 0.1532 kilogram of steam per kilogram of feed water. So this is the final answer of the first part. Now in the second part we are finding laws of exergy per unit mass. Here we find laws of exergy per unit mass. So for loss of in exergy per unit mass, loss of exergy per unit mass is equal to loss of exergy of steam. This is loss of exergy of steam. Loss of exergy of steam is equal to, this is denoted by E1, H1 minus H3. Basically this is uh, this is simple diagram. This is the steam entrance to the feed heater. This is the feed water entrance, and this is the exit of steam plus feed water. So and after entrance and exit, how many exergy loss this steam find at this point? Enthalpy is H1, entropy is S1. At this point entropy is enthalpy is H3 and entropy is S3. So loss of exergy per steam is equal to, this will be equal to H1 minus H3, H1 minus H3 minus atmospheric temperature T0 into S1 minus S3. Put the values. So H1 is equal to 2796 minus 845 kilojoule per kg minus atmospheric temperature is 293 Kelvin into S1 minus S3. S1 is 6.452 minus S3 is 2.315 kilojoule per kilogram per Kelvin. This Kelvin will be cancelled with this case. So final answer will be kilojoule per kg. So loss of exergy of steam per unit mass is equal to, final answer will be 734.9 kilojoule per kg. Per unit mass means per kg, and this is denoted by E1. So this is the final answer of second part. Now we are solving third part. So in third part we have to find effectiveness. So for effectiveness, first we find gain in exergy. So again I draw the diagram, simple diagram. This is steam entrance, this is feed water entrance, this is steam plus feed water exit. And this process from steam to this exergy losses, which is 734.9 kilojoule per kg. This is exergy losses. But from feed water to this exit, this is gain in energy, exergy gain, yeah, or gain in exergy. So for effectiveness, first we find gain in energy. So exergy, so gain in exergy from feed water to mixture, from entrance to exit. Entrance will be feed water, because from feed water to this mixture exergy is increased. So gain in exergy is equal to H3. Here the enthalpy is H3, here the enthalpy is H2. So H3 minus H2 minus T0 S3 minus S2. Now putting the values in this is E2. So H3 is equal to 845 minus 546. H2 is 546 kilojoule per kg. Minus T naught is atmospheric pressure, which is given to us as 293 Kelvin. S3 minus S2. S3 is equal to 2.315 kilojoule per kilogram per Kelvin. Minus S2 is 1.635 kilojoule per kilogram per kilogram per Kelvin. So gain in exergy is equal to 99.5 kilojoule per kg. This is simple calculation. This Kelvin will be cancelled with this Kelvin. So final answer will be in kilojoule per kg. Now for effectiveness, formula for effectiveness is loss in exergy divided by gain, increase in exergy or gain in exergy divided by loss in exergy. Increase or gain in exergy divided by loss in exergy. And increase in exergy is denoted by E2 and loss is denoted by E1. But mass is given to us. Increase or gain in exergy, mass of is denoted by mass of feedwater. Mass of feedwater, so this is MFO. And this is mass of steam entry. Mass are given, so MF is equal to 1 kilogram multiplied by gain in exergy is 99.5 kilojoule per kg, and mass of steam is equal to 0.1532 kilogram multiplied by loss in exergy is equal to 734.9 kilojoule per kilogram. So simply calculate this. So effectiveness will be equal to 0.881, and in percent multiply and divide by 100. Multiply by 100, and per divide by 100 we use percent sign. So finally the effectiveness will be equal to 88.1%. This is the final answer, and hence the problem is solved. And for more videos, please like and subscribe my YouTube channel. Thank you.